Hello everybody, welcome. Thank you for joining. And as we was mentioned, it's a very exciting time for us, being under the MSC software umbrella again with the Simufact software. So today I'm going to talk about our capabilities for riveting, especially self-piercing rivets, very strong application. Show you the software, show you some other examples of high-speed riveting, and then some cutting and punching application, and leave some time for question and answers. Before I dive into the topic, I want to take the opportunity to talk a little bit about the Simufact software. So we have two software products, Simufact.forming and Simufact welding. And through some visuals, I want to give you a bit of an idea of what type of manufacturing processes you can simulate with this. So on the left side, you can see the metal forming applications, cold forming, ring rolling, hot forging, open die forging, some sheet metal forming for the electronics. Left bottom corner, that's a piercing, self-piercing rivet application that we're going to talk about in a lot of detail. Then a hot stamping application. And on the right side, you see some examples for our welding product, focused on automotive or the heavy industry type applications. And then we have a module called Simufact Premap. This stands for Prediction of Material Properties. And this can be used within both the forming and the welding application to look at the effects of the forming process or heat treatment on the material properties. So looking at hardness of the material or the grain size, phase transformation, those type of things. Now the evolution of the applications of the Simufact family, it all started really in 1995 when we started doing bulk metal forming applications. Look at think about fastener and manufacturing, how do you form a bolt, and that has evolved over the years into very complex type of simulations through a rolling application, swaging, piercing, closed die hot forging, and then some more rolling application of threads that you see on the right hand side. After that, there was a big push, big focus on development of capabilities for sheet metal forming application, and then you should think about what we call the thicker sheets, thick sheet metal forming. So we do sheet metal forming using a volume approach, using hex or tet elements. You see some very nice applications in the pictures. On the third layer, you see the topic of today, which is joining, and joining is kind of combined here with the welding application, because you take pieces of material and you want to join them together. You can do that with mechanical joining, like piercing or clenching, or thermal joining, which is done with the welding software. And then the top, that's a big focus of us today, is the process chain. To simulate the complete manufacturing process chain, and then also push that after the manufacturing process is done, push it into a follow-up analysis to look at durability, fatigue, and VH type characteristics of the product or part that has been made. This slide shows the GUI of the Simufact forming software, and the welding software looks actually very similar, same concepts. The key, and this is why people really like to use our software, is that the GUI, the graphic user interface, it's aligned with the metal forming process. So you talk about presses and dies and workpieces. So it's easy to understand for the designer, process designer, what he's actually setting up, what he's modeling. And we work very hard to streamline the workflow, the way you work with the software and the way you insert the software in your other finite element analysis activities is streamlined as much as possible. So the key is it's a process-oriented GUI. On top of that, it's very easy to learn. It's actually a lot of fun to use it. We get that feedback a lot. So when we do a training, an introduction training, it's just 2 days. And after 2 days, you're up and running with it and running your processes with it. So the last topic is key because it's easy to define a simulation. It's easy to then to simulate it. But what's most important, it's very easy then to make a variant on your metal forming process. You just make a copy of it, replace the die, replace some settings, run it again, all in the same environment, and then you can do side-by-side comparisons in a very intuitive manner. So let's look at the self-piercing rivet application. And I think of all the type of joining applications, I would say this is one of the most important ones today in a lot of industries. So let's talk about the process itself. What is it? Well, it is a mechanical joining operation to connect 2 or more layers of sheet material. The material can be either metal or plastic. In most cases, I would say it would be a metal like steel or aluminum, and can be with or without glue in between the layers. And let me play this animation. So here we see the rivet. There's a blank hole or a punch, and it's going to pierce. That's why you call it a piercing process. It's going to pierce through the top layer, and then it deforms the bottom layer, and it pushes it into a die. And this creates a joint. So there's no melting, no thermal, no nothing. You're just deforming the material to create the joint. And that's why they call it mechanical joining. Now, what's the challenge with self-piercing rivets? The challenge is that if you have a given stack of layers, can be 2 layers or 3 layers or even more, the designer, the joining process, has to decide what's the best rivet and die combination to create a good joint, a strong joint. And these are some of the aspects of a joint that they need to look at. If you pierce through the top layer, but the bottom layer needs to be pushed completely in the die, you don't want to go too deep, so you have a bottom thickness. That's a characteristic of a joint that makes it good or bad. This web or bore needs to fill up completely. There's an undercut. This is basically how far the rivet flares out to give a good joint. And then you have the alignment. You don't want to push it in too far. You don't want it to stick out, and there's a gap depth. So this is a cross section of an actual, a real joint, the coupon that was made. So the business case for simulating self-piercing rivet is to reduce the number of test coupons to determine what a correct die and rivet combination is for a certain stack of materials. And here we just see 3 pictures, one of 2 layers, one of 3 layers, and one of 2 layers, but was a high-speed riveting application. And the number of possibilities is actually quite amazing, because sometimes for a certain stack-up, the engineers, they have to literally go through 100, 200 combinations of rivet and die combinations to determine the optimal one. So if you can reduce the number of test coupons to come to the best combination using simulation, that's really why people want to simulate this. Now, instead of just looking at the characteristics of the joint, like how is it shaped, how does it look, you can also simulate the strength. So you can do a shear tension test in the software, and you can then also do cross tension test. So these are some of the tests that they do experimentally that can also be simulated. And then you have the force stroke curve that's shown here as well. So let's look at the software for a second. I'll open it up. And here's the model of a self-piercing rivet process with 2 layers. So I'll walk you through the model setup to get an idea of how the software works. So here we have a process tree. It's called SPR, and there's a press, and this press moves the punch down with a certain velocity. So when I click in the process tree, it highlights in the graphics what object I'm looking at. So then we have the rivet, which is inside there. We have the blank holder. We have a die. The material is pushed into that die cavity. Then we have a lower sheet, highlighted. You have a lower support that represents the rest of the sheet that we don't model as a deformable body. And then we have the upper sheet and the upper support, again, that represent the rest of the sheet that we're not modeling as deformable. Now, you see that we're working with 3D shapes, even though we're doing a 2D simulation here. And you can actually check what the 2D model is by double-clicking on this icon in the process tree. And then you see here the cutting plane. This yellow plane cuts through the models, and you can do a preview of the 2D model that we're going to simulate. Here we have the punch, the blank holder, the rivet, the upper sheet, lower sheet, and here's the die cavity. So the software supports both 2D and 3D type simulations in one environment, and you can use this process tree to just look at one process, or you can then copy it to make a variant of the process, or you can do multi-stage processes to go from one stage to the next, and you can even switch from a 2D stage to a 3D stage. So the software is very flexible to set it up, and everything carries over easily. Then let's drill down a little bit in the process tree. So it's very nicely organized. You have the punch, highlight again. So the punch is just the geometry, the friction, and some temperature data. Then we have the rivet. The rivet is actually modeled as a workpiece here. So it has a mesh, geometry, material, temperature data, and a remesh object. And if I look at the mesh, you see we're using the quad 3 mesher, and we have a very nice mesh for the rivet. Then we look at the blank holder. The blank holder actually has a spring attached. So if I make the punch transparent, you can actually see the spring. It's sitting in there, and the spring is connected between the blank holder and the punch. So you can define springs between multiple tools, multiple dies, which gives you the flexibility to make complicated tooling stack-ups. Then we look at the die. It's just a shape, nothing special. Then we have the lower sheet. Again, has a mesh, geometry, material. If I open up the mesh here, it's just a simple mesh initially, 2D advancing front quad mesher. And then we go to the lower support and the upper sheet. And the upper sheet I want to talk a little bit more about because it has an initial mesh that you see here. But we know that in the simulation we're going to cut through the upper sheet. So we have several mechanisms to simulate the cutting through. One option would be to introduce a damage law, like Cockcroft-Latham, and elements will just be removed based on a damage value. Another approach would be, and that's what we use here, is to use a splitting algorithm, where when the minimum distance has reached a certain value, we just split the piece in two. So in the little drill down, this is how the process tree is set up, and this is all done by drag drop. Once you have the geometries available, you literally set up this process in a few minutes. And then you can look at the results. So I can open up the result tree, and I can first look at just an animation. Let me turn the spring off, zoom in a little bit. See, this is, and then here you have the animation that I showed you earlier, but now it's just live in the software. And you see that even though we do a 2D simulation, you can actually visualize the results in 3D. You can do full 3D 360, or you can do, like in this case, 240-degree angle view. It's just to make it easier for people to understand what they're looking at. Most people understand 3D pictures better than 2D pictures. And now see how we cut through it. And we're pushing the material into the die to create the joint. And once it's fully pushed in, and we're filling up the die here, you see some gap between the layers where it's closed off, and then the punch is pulled back. Okay. Now, if you want to look inside the material, I always prefer to look at 2D. I can just double click. And now you can look at the plastic strain. And the blank hole grabs it, and you just cut right through it. You see this gap here? Sometimes this gap is not closed between the layers. Then you have a bad joint. But in this case, it pushes it through pretty good. And then the last result I want to show you is of course, the force. You can look at the force requirements, which of stroke versus force. And if I play the animation again, you can see exactly when we're starting to build up the force, and it starts to go up very rapidly once we're starting to push the material into the die cavity. So these are some of the results that people then look at with simulation. And let me go back now to further discussion in the presentation itself. A very nice example of a riveting process is high-speed riveting. It's a very kind of a new application. So here they shoot the rivet at very high velocity into the material. And some correlation studies were done. So here you see an experimental result on the right side versus the simulation. And for this you need to use a dynamic simulation. This particular case was also done with a layer of glue. And you can see it's dynamic because at the end of the process, when the rivet comes to a rest, it's actually oscillating a little bit. We do everything implicit. So all the simulations shown here using implicit, and here we're using implicit dynamic simulation. There we hit it. The solver underneath the Simufact software is a special version of the Mark solver. So those of you who are familiar with Mark, you know the core technology that's being used here. And then several additions were made to make all these simulations run smoothly and robustly. Next we have blind riveting. And here I want to talk about this concept of a complete manufacturing chain, even going to the follow-up process of a loading and failure analysis. So the steps that I'm demonstrating here is we start by cutting a slug to form the rivet, so cut off a wire of material. Then we actually do the cold forming process of the rivet, which is a 3-stage process. Then we use that to do blind riveting of 2 layers. And then at the end, we move the results of that forming simulation into a failure analysis of the joint with the regular Markov method. So this is the first step. So you have a wire, metal, and we simulate the cutting of the slot. So that's the part at the end, which is used to then make the rivet. It's important to simulate this if you want to go to a very detailed analysis, because as you see in the cross section, you get a buildup of stresses, and the shapes are different. There's some roll off at the top, and there's a little burr formed at the bottom of the cutting process. So then we cold form the rivet. So there's an extrusion process, first stage. There's an upsetting of the head, second stage. And then here is the cutting of the center part, because with the blind riveting, we need to have a rivet that goes all the way, has a hole in the middle. Then we go to the riveting process itself. I'll play this again. So here you see how this is formed to connect the two layers. I'm not showing it on these slides, but a study was done to simulate this process with the stresses that come from the forming process of the rivet and without the stresses from the forming process. And for this particular example, it was crucial for the correct result to take into account the forming stresses coming from the stresses from the forming process. And then we do the loading analysis. So this result is then moved into the regular CAE analysis, so go from Simufact to other tools, in this case a mark, and a loading analysis was applied to see, well, how strong is this joint? And this can then also be carried into other type of analysis of the MSC product family. Then the last slide I have is it's about blanking punching. Here you see a punching process, and this is a nice example where we use the damage approach. So let's play it again. You see the punch coming down and automatically remeshes, and then the software calculates the damage that's built up in the material. We have several damage models exposed in the GUI, and then once the damage reaches a certain value, we use element removal technique. Now the elements are removed and a crack starts to propagate through the material, and then it breaks off into two pieces. Well, people use these type of analysis to study not only how the material itself breaks, but also what the die wear of the tooling, because the punch wears faster or slower based on the gap between the punch and the die or the radii of the dies. And those are all things that you can then study with the software and run some variants on. So that completes what I want to present today, and Srinivas will now take control back and we can answer some of your questions.